Thanks a lot for the invitation. It's always a great pleasure to be here. So I will talk today about the L2-Stokes theorem on complex varieties. So Stokes theorem is something you all know very, very well. For instance, so if something has compact support, then Stokes theorem gives us partial integration, at least if we are dealing with the infinity forms. So let's, for some motivation, consider a domain in Cn, and I take smooth PQ form and a smooth PQ plus 1 form with compact support. So compact support and smooth is denoted by this D as usually in the theory of distributions or currents. So let me put one version of Stokes. If I take d bar of f wedge g conjugated, and this becomes a 2n form. So this is a 2n minus 1 form. It becomes a 2n form with compact support, and then by Stokes theorem, it's the same as the integral over the boundary of omega, or something which is smooth and close to the boundary, and we have that this is zero. So this was maybe analysis 2. And now what happens if we weaken the assumptions on f and g? So let me, for example, take f and d bar f in the sense of distributions in L2 log. So again, PQ and PQ plus 1, and G and the adjoint of d bar of G again in L2, but with compact support. Then this here remains valid, at least in the sense of distributions, and you can apply d bar to the two forms here. So you get partial, you get two integrals, and you have partial integration by this integral being 0. So then, if we have these assumptions here, then star is equivalent to d bar f paired with g in the L2 norm of integration is the same as f d bar star g in L2. So Stokes theorem tells us that we have partial integration in the L2 sense if all the forms under consideration are L2 and one side has compact support. Okay, this is something very classical. Now the question is what happens if, so what happens if omega is a domain inside, oh, yeah, okay, I have compact support here, so it doesn't matter if omega is unbounded, but let's make it bounded. Inside X, and X is a singular variety which carries a Hermitian norm, so that L2 spaces make sense. But if we consider omega inside a variety X, then we have problems at the singular set of X. If it's inside a manifold, then the same thing holds as in Cn. But if X has singularities, then we have a problem. You can think of it in the following way, and then it's sometimes, when it's somehow closer to really thinking of Stokes theorem. So X is singular and Hermitian. So we have a metric on it. Usually this will mean that X carries a metric which comes from the restriction of a metric in local embeddings, so from ambient metrics. So they don't blow up or do something strange at the singular set. It's just the restriction of a usual Hermitian metric of the ambient space in local embeddings. So omega sits inside. This looks smooth again, but it shouldn't be smooth. And then we have here a singular set of X. So if we want to do or apply Stokes theorem now, then let's say the forms have compact support. So the compact support is somewhere here. We can take a boundary here, which is somehow smooth here in this part, so that doesn't matter. But the question is partial integration over the singular set here possible? For example, you could apply Stokes, just maybe make it like this, on such a domain here, and you stay away from the singular set. So you apply Stokes here. Here we have the compact support thing, so here everything is zero, that doesn't appear. But what remains is some boundary integral over this boundary here. But there is a little hope that this doesn't disturb us too much, because the singular set in a varieties of real codimension 2, complex codimension 1. So this here is, so if you consider the classical Stokes in Cn, then the boundary which appears in Stokes theorem is of real codimension 1. And here we have now something which is of real codimension 2, so it's smaller. And that gives us a little hope that Stokes theorem, as it is written here, in the sense of partial integration, could work. But actually it doesn't. I will show you some counterexamples and some ideas to overcome this problem, so that the counterexamples disappear under some assumptions. So about the L2-Stokes theorem on complex varieties. So one says that L2-Stokes hold on a variety for d bar exactly if this here is true. It will appear later again on the slides. So in order to study L2-Stokes on varieties, we have to make clear how the differential operators on the variety work. We are considering differential forms which are square integrable on the regular part of the variety. So this regular part of the variety becomes incomplete. And this means that we will have to consider different closed extensions of d bar on smooth forms with compact support. The same for the adjoint operators. Then we will study how the partial integration will look in the setting. So that will be precisely this thing here. And then we will discuss a little bit how one could prove the L-Stokes theorem, for example, for functions. So for functions, if f is a function, then this thing here will actually hold. For the d operator, but not for the d bar operator. So maybe I should say this here. You can as well put here, instead of d bar, you can put d, and then you have d here and d star here. So you can discuss everything for the exterior derivative, the d operator, or for the d bar operator. And we will discover that they behave differently. We will study this a little bit on the level of functions, and then I will say some words of about forms of higher degree. So as I said before, let X be a Hermitian space, and throughout the talk always of dimension n. For example, if you don't like arbitrary Hermitian spaces, then just go into Cn, take a variety, an affine variety in Cn with a restriction of the Euclidean metric, or take a projective variety with a restriction of a Fubini study metric. Then I denote by Lk and Lpq the sheaf of germs of K forms or PQ forms, which are L2 log with respect to X and L2 up to the singular set. So let me return to my picture here. It's abstract. It's abstract. So it is invariant under biholomorphisms. Yes, yeah, and a restrict of the ambient space. If you take a different embedding, which is biholomorphic, then you get equivalent notions. This is okay. So L2-log means, well, this is not, that it should be, if something is L2-log on this domain here, means that it should be L2 on any compact subset. So if you approach here, it is L2, so it cannot blow up arbitrarily if you approach the singular set, but it is an L2-log, so it can do whatever it wants if you approach the boundary of omega. Will it ever matter? It's a good question. At some point it matters, at some point it doesn't matter. It's the same thing as usually. So in general, the theory is also for non-normal spaces, and many of the statements are also for non-normal spaces. But if it's normal and you're talking about something which is Debye closed and the regular part, and it's normal when it's a holomorphic on the regular part, and if it's normal, then it extends to a strongly holomorphic function. So in this sense, it matters at some points, but the theory in general is also for non-normal spaces. Strongly holomorphic functions on singular varieties are the holomorphic functions which come from ambient space as a restriction from ambient space. Bounded. Weakly holomorphic functions on singular varieties are functions on the regular part which are holomorphic and which are bounded. Yeah. And they come, you can define weakly holomorphic functions in terms of a resolution of singularities, and you consider push forward of functions from above. And we will here also consider functions which are holomorphic on the regular part and just L2, which is a priori a little bit weaker, or you could consider holomorphic functions which extend continuously in the singular set, that also appears at some point, or just holomorphic on the regular part with arbitrary singularities. Yes. A complex variety is a complex space. Yes. Did I? Usually, it should be reduced. So, but actually we do not really care, because we make analysis on the regular part of a variety, and we don't care if there is an additional structure which is unreduced. It doesn't really matter for us. But yeah, when I'm talking about when holomorphic functions, then I should assume that it's reduced. Usually when people talk about Hermitian complex spaces with a Hermitian metric on it, then it's usually assumed to be reduced. Say it's reduced, yeah. Okay, the dW, so the W stands for weak, should be the D operator in the sense of distributions, and D bar W analogously the D bar in the sense of distributions. When I denote by CK and CPQ the L2-log forms, so that the D of it is again L2-log, and by CPQ the L2-log forms, so that the D bar of it is again L2-log. So and this is what you also want here, in order that these products make sense. You want to have the D bar of F in L2 as well. And yeah, later we will also consider formal adjoints or adjoints with this L2 property. Okay. So then you can classically define the cohomology groups with respect to the de Rham operator, or with respect to the Dolbeault operator, or if you consider forms with compact support, when you get the compact cohomology. Okay. the d bar W operator is pretty useful for forms of degree n q. So n is the dimension of the space. So these are, let's say, forms of high degree in the first component. Just recall that on manifolds and the same on varieties, and even worse, on singular spaces, there is a huge difference between considering PQ forms for different values of P. So NQ forms behave considerably different than 0Q forms or than PQ forms for P somewhere in between. If on the level of n forms, you take the kernel of d bar W, so these are the L2 n forms, which are holomorphic in the sense of distributions on the regular part. Then you get the Grauert-Riemenschneider canonical sheaf, as I said, of holomorphic square integrable n forms. And this was introduced by Grauert and Riemenschneider, and it is actually a coherent analytic sheaf, which is a priori not so trivial. Another interesting feature is that the d bar W equation is locally solvable for NQ forms, even in singularities. So in regular points, it's clear the usual solvability for d bar, but it's solvable for NQ forms, even in singularities. This is essentially due to Pardon and Stern in the 1991 paper. So you get here a fine resolution of the canonical sheaf of Grauert and Riemenschneider. I don't know if maybe it doesn't appear. So why is the canonical sheaf of Grauert and Riemenschneider coherent? If you take any resolution of singularities, then the Grauert-Riemenschneider canonical sheaf is just the direct image of the canonical sheaf on the resolution, and by Grauert's direct image theorem, it's then coherent. This is true because the L2 property, for n forms remains invariant under modifications just by the transformation law. So maybe I should write it. So by the transformation law, the L2 norm of n forms can just be computed as omega, omega conjugated, for example, and then the transformation law says that if you push forward this, then it remains the same. So the L2, so this is the L2 norm for n0 forms or 0n forms. It's the same. Okay, so this is interesting because here you have a coherent analytic sheaf. This is sheaf cohomology here, without or with compact support, and then the abstract Dolbeault theorem tells you that if you have a fine resolution, so these sheaves here, that is not hard to check, admit a partition of unity, so they are fine. And then you can express the cohomology of the Grauert-Riemenschneider canonical sheaf in terms of the Dolbeault cohomology groups, so in terms of some differential equations. And if you use this, moreover, then you can make also a connection to the cohomology on a resolution, which is somehow a smooth model for X and its cohomology. Okay. Now we have to consider another operator, namely the strong L2 d bar operators. So something is in the domain of the strong operator, which is indicated by an S here. If it is in the domain of a weak operator, so we start with something which is L2 log, and d bar in the sense of distributions is again L2 log, and then we say that this is also in the smaller, it is actually really smaller, domain of the d bar S operator, if it can be approximated in the graph norm, so this here is approximation in the graph norm, by forms with support away from the singular set. Okay. So And this clearly gives you the idea that then partial integration over the singular set should be possible, because if I can approximate something in the graph norm by forms with support away from the singular set, then I can move the application of Stokes theorem into the area where the thing is zero in the sequence, and then partial integration works without problems. So this operator obviously has something to do with the fact whether partial integration works or not. Okay. I denote by fk and fpq. So the d operator is defined analogously as the d-bar operator. I define the d operator if f is in the domain of d in the sense of distribution, and if it can be approximated by forms with support away from the singular set in the graph norm for the d operator. So completely analogous. Fk, Fpq should be the domains of these operators. And as before, I set up the classical Dolbeault cohomology for the d by s operator. The same for the exterior de Rham derivative in the strong sense, and the cohomology groups with compact support. And here at this place, I will give some statements about these groups here a little bit later in the talk. They are, well, there are different results than for the d-bar in the sense of distributions. So let's think a little bit about these operators from the point of view as functional analysis. So you can consider smooth forms with support away from the singular set. Then the strong operators are the graph closures of these operators acting on smooth forms with compact support. And the graph closure gives you the minimal closed extension, because all closed extensions have closed graph, and if you are considering a closed extension, then it must have closed graph. So the smallest one, the minimal, you are getting just by closing the graph. And yeah, the weak operators are the maximal closed extensions, because if you take a maximal closed extension, it still must be a differential operator in the sense of distribution, and that is the weakest condition that you can have. The interesting thing about these operators, about the weak and the strong operators, is that they are dual in an L2 sense. So if you take the formal adjoint operator, you can always, so maybe let me make it here. I write, maybe I just make it for d bar, and for the d operator it's analogous, because for the d bar I can I have a different letter for the formal adjoint operator. So if you take, this is the formal adjoint of d bar. If you consider it on smooth compact forms, then by definition the d bar in the sense of distributions is the adjoint of this operator. So, and we can take the dual again, then we get that d bar star is theta compact dual bidual, and in a Hilbert space, so the adjoint operator is always closed, we end up by just the closure of the graph. So this is the formal, a strong extension of the formal adjoint of the d bar operator. So this works pretty easy in Hilbert spaces. And this is classically contained in the classical Ruppenthal theory, for example. It becomes here a little bit more complicated because we are considering operators in L2 log spaces, that is just a Fréchet space. And then in the dual sense, we have to consider L2 with compact support, that is just an LF space. And yeah, this is not so trivial. You have to apply many, many times Ries representation and Hahn-Banach and go back and forth. So, however, we have these duality notions, and from that, from that, one can deduce various notions of their duality between the Dolbeault cohomology groups. That will appear a little bit later at some points. Okay, and in contrast to the D-bar operator in the sense of distributions, the strong D-bar operator is useful for zero Q forms. For example, the kernel of D bar S on functions. So you take holomorphic functions on the regular part of the variety, which are L2 up to the singular set, and in the kernel of the D bar S operator, so they can be approximated in the graph norm by smooth forms with compact support. And then you end up with weakly holomorphic functions. So holomorphic functions which are actually bounded if you approach the singularities. So this is also not trivial. So the kernel of D bar S on the level of functions are the weakly holomorphic functions. This is a usual notation for the weakly holomorphic functions on singular varieties. And another interesting thing is the obstructions to solving the D bar S equation locally for zero Q forms. So there are obstructions in general for NQ forms and the D bar W. We had solvability, so the Poincaré-Dolbeault lemma, but here we have in general obstructions, and they can be described in terms of a resolution of singularities, and the obstructions disappear if and only if the singularities are rational. That will also appear later again. So now the functional analysis, which I had already on the blackboard to the right. F in the domain of the D operator in the sense of distributions is in the domain of a strong operator if and only if you can do partial integration. So there are two directions. If you can approximate it by stuff with support away from the singular set, then you can make partial integration by the procedure I just explained. The other way around, it's more or less inside the definition of these operators and by the dualities and so on. So you also get the other direction if you have partial integration. Then by definition, you get that something is in the domain of a strong operator. Okay, let me see. Something in the domain of the weak is also in the domain of the strong if and only if you can do partial integration. No, this is correct. Okay. So one could ask, is this not always possible? Because the singular set is of real codimension 2. That gives you some hope that it could always work. And the same for the D bar S operator here, the same something in the domain of D bar weak is in the domain of D bar strong if you can do partial integration. So one says that the L2-Stokes theorem holds if the strong operator equals the weak operator for the Ram operator and for the Dolbeault operator. So this is a theorem that sometimes it does hold and sometimes not. It holds for domains in Cn or in complex manifolds. The question is, does it hold in general? So if you start with something in the, maybe here in the domain of the D bar weak, can you always do partial integration? So is it always also in the domain of the D bar S operator? This is the question. And the answer is in general no, but let me start with some kind of folklore conjecture that appears in many older papers from differential geometry and global analysis, but obviously that does not exist to prove. So it's some kind of folklore conjecture, but it holds for the Rahm operator on complex projective varieties in all degrees, so for PQ forms of arbitrary degree, but actually there does not seem to be a proof anywhere. But some people said, okay, it's true, but no references are given at all. Okay, at least if we have a projective variety with only isolated singularities, then the L2-Stokes theorem holds for the de Rahm operator in degrees not equal to some middle degrees. So you have degree for de Rahm from 0 to n minus 1 to n, and there's a gap in this theorem in the middle, and it holds for d bar if p plus q is not one of these middle degrees. The results are sharp for d bar. So if p plus q is equal to n minus 1 or equal to n, then there are counterexamples to the L2-Stokes theorem, but I'm not aware of counterexamples for these cases here. So there is some hope to prove it for isolated singularities also if k is one of these middle degrees, but for the d bar operator there is no hope. We have counterexamples. I will show you one in a second. Okay, so if one would like to prove the L2-Stokes theorem, there's a pretty straightforward way, namely take the form, cut it off away from the singular set with a sequence of cutoff functions which approximate the identity, and look if the thing does not converge in the graph norm. This is the straightforward idea. I take a sequence of cutoff functions vanishing away from the singular set but approximating the identity, so getting the support approaches the singularity more and more and more and more. I just cut it off by this, and when I ask a question, doesn't it converge in the graph norm? Maybe it doesn't, then everything is fine. And actually, there are nice cutoff functions with support away from the singular set, converging uniformly to one on subsets of positive distance to the singular set of X, and they behave, the D of it and the D bar of it behaves good in the L2 sense. So the problem is, you can imagine if here is the singular set of X and this is X, you start with cutting off like that. This is maybe, what did I call it? Mu. This is maybe mu1, and then this is mu2 and mu3, and the slope gets larger and larger. So we don't have a problem with these functions, but we have a problem. We have a problem with the derivative of it getting larger and larger here. But it is uniformly bounded in L2, and it is just restricted to a small area, so it converges by Lebesgue's dominated convergence to 0 in total. This is a pretty helpful thing, but still not perfect. As you can see, maybe I should write it here again. Okay, what is clear by Lebesgue's dominated convergence, if you cut it off with these functions here, then by Lebesgue in L2 this goes. If you consider the bar of this thing, then you have a good part and a bad part. So for convergence in the graph norm, this here is just again by Lebesgue in L2, that goes to d bar f. So what we need is that this here goes to 0. But f is in L2, and this goes to 0 in L2. So by Hölder, the whole thing goes to 0 in L1, okay? But it should go to 0 in L2. This is a problem. The problem disappears if f is not just in L2. If f is bounded, then the problem disappears when this error term goes to 0 in L2, because we have the d bar of the cutoff stuff going to 0 in L2, and this here is bounded, and when by Hölder it goes to 0 in L2, and we are fine. This here? No, this here goes to 0 in L2. It's you really have to look how it is defined and when you need to make computations. Yeah, it's a specific construction. Arbitrary cutoff functions will not work. It is a specific construction. So there exists such a thing. I didn't want to put it. Okay, no. It behaves like a log of the distance to the singular set, and then you can make the computations. And you get that the L2 norm is uniformly bounded, and it goes to 0 pointwise, and then it goes to 0 in L2. Yeah. It's hidden in where exists such a thing. Yeah. Okay, so if it is bounded, then everything is going well. So bounded forms in the domain of the weak operators are also in the domain of strong operators. This is at least something that we know. So you could have the idea. So if you know, you can approximate bounded forms in the graph norms by forms with support away from the singular set. Then the next idea is, okay, maybe in the first step I approximate by bounded forms, and then in the graph norm. So this is actually possible for functions. So if f is a function in L2 log with maybe d bar or d in L2 log, consider, then you can just make this construction here. So this is bounded. If you take just the norm, then it is, or if you, yeah, here's the square. So this is bounded, yeah. And you can compute that these Fn converge in the graph norm to F the weak F. So this is an easy computation. You just at some point there appears the d of this here, but then you use that the df is in L2, and it works well. Okay. So this construction on Hermitian complex basis, the L2-Stokes theorem holds for the exterior derivative d, the de-Rham operator on the level of functions. And you could ask, well, how about the same procedure for the d-bar operator? And I can tell you that this will not work. So for the d-bar operator, it doesn't work. The reason is pretty simple. If you consider the d operator, then you will need to consider d of f times f bar, and yeah, this behaves like f which df, and both are L2, and this will be enough. If you make the same for, if you have that df is in L2, if you take d bar of the same thing, then you will have f wedge d bar f, which is fine, but you will also have something f wedge delta f, and if you just know that d bar of f is in L2, but you don't know that delta f is in L2, then you have a problem. So this is why the same procedure doesn't work for the d bar operator. And no other procedure will work, because on the other hand, we can prove that this actually, you can do whatever you want, it will not work, because there is a counter example. So the DS closed functions are precisely the weakly holomorphic functions. I mentioned this. I mentioned this before. This is not trivial. It's to explain this thing here is another talk on its own. But just let's take it. So if something is in the domain of a DS operator, then it's automatically bounded. So you can think about a function which is in the domain of a d bar w operator, which is not bounded. And I can give you one in a very simple example. And for this, actually, yeah, yes, if the space is normal, then the two operators are the same, yeah, by normality. But here you can have that it's, if the variety is not normal, then you have an example. You have an example here. I will not make all the computations in detail, but I would like to give you some kind of idea. From the picture. Okay, which way round? So C and W, and W behaves like C to 3 over 1/2. So it's a cusp looking like that. So this is pretty convenient. Very unusual for a singularity, because this has a tangent space even in the singular point. Because yeah, what you get from this, if this is the C direction, this is the W direction, is that the C on the variety X is similar to 1, because the tangent space is just the C line. Maybe let me put that's one of the nice things of irreducible curves, that they have a tangent space. Okay, so this is the tangent space. So in principle, if you just think about analytic properties for integrals, then the variety close to a singular set, okay, it's double sheeted, so there are two sheets, but in principle it behaves like the complex line in the C coordinate. So let's consider holomorphic functions on the regular part which are not strongly holomorphic. One is C over W. It has a pole. It has a pole in the singular set, but the pole is pretty harmless. It's the pole is pretty harmless. It behaves like 1 over the square root of C, and this is clearly square integrable, because if you take the square, then it has a pole of order 1, and the variety behaves as C, and you know in C it's like R2, you can integrate a pole up to order 2. So this behaves fine. It's holomorphic on the regular part, and it is L2, and it is in the domain of the d bar W operator, because it is holomorphic in the sense of distributions on the regular part. That is what we want. Okay, and it is obviously not bounded, because it has a pole in the singularity. If it were also in the domain of a d bar S operator, then it would need to be bounded. So here we have d bar W holomorphic functions which are not d bar S holomorphic. So here the d bar W and the d bar S operator are actually really not the same operators. If you put W over C, then you get the square root of C. This is a classical thing from the Riemann surface theory, that you know this is This is bounded. This is a weakly holomorphic function, but it is not strongly holomorphic because it's not the restriction of a holomorphic function on some ambient space. Just to complete the picture here. Okay, but we had some theorem of Pardon and Stern saying when the operators are the same. So let's check if we have a contradiction to their theorem. No, this is not the case because we have here P plus Q is just 0, but the dimension is 1, so 0 is dimension of x minus 1, and this is one of the cases they excluded in their theorem. So it's absolutely okay, and actually their work is proper, at least from my point of view. So what can one do if we want that the L2-Stokes theorem should hold? The reason is behind all this is the question, what can one use instead of smooth forms on a singular space? So what you want is a replacement for smooth forms which has all the nice features that you know from smooth functions. For example, you want to have partial integration because, for instance, you want to solve the bar equations and so on, and you know by Hermann estimates, you always have to do partial integration if you want to solve differential equations. So you want to get to as close as possible to C infinity, so you want that you have partial integration. So the question is, what can you do to get it? And the idea is to work the Sobolev spaces instead of L2 forms. So the approximation procedure I just described by bounded forms had the problem that we had to consider the bar of the norm of f squared. And then delta f appears as well. But if we have a delta f is also in L2, then everything should work fine. If we go to forms of higher degree, one would want something like the bar of it is in L2, and the adjoint of the bar operator of it is in L2, and maybe one has also to consider other partial derivatives. So what you could be tempted to conject is that something is not just in the domain of the D operator, but also in the domain of a joint operator, that it's then in the domain of a strong operator. This is something like elliptic regularity in some sense. So let's check the counterexample, maybe. So if we take D of our counterexample, then you can compute that this is what you plug in here. I don't want to do all the computations here. So what you plug in is 2w dw is 3c squared dc, and you get that the exterior derivative of this, at least on the regular part. So you shouldn't take the derivative in the singularities when you get something like a Dirac measure. But we consider our forms and functions just on the regular part. So this is D on the regular part of the variety. Then we end up with this here. In the L2 norm, so DC, we have like 1. This is fine. But W squared is like C3. And C3 is not integrable over the complex line. So the counterexample is not in W1. It has a d bar. The d bar of it is 0, which is L2, but the delta of it is not square integrable anymore. But if you consider functions which have a delta of it square integrable, then the cutoff procedure would work. Okay, so this is the idea about partial integration, some counterexamples, and that maybe it works if you go to Sobolev, if you go to Sobolev spaces, and the whole thing similar holds for forms of higher degree. Let me maybe put it here. So there are counterexamples for all degrees which were excluded in the Pardon and Stern thing. For example, if you consider rational singularities of complex surfaces, they are classified as the Duval singularities of type Dn, E6, E7, E8, for example. Then the d-bar W equation is solvable at the An singularities, but for 0-1 forms, there are obstructions at all the other rational double points. But on the other hand, we know that the d-bar S, the strong d-bar, is solvable in rational singularities. They are all rational. So in these cases here, the d-bar W equation is not the same as the d-bar S equation. But again, if you assume that the 0-1 form is not only in the domain of the exterior derivative, but also the d star of it is in L2, then these obstructions also disappear. So here is the same phenomenon as on holomorphic functions. D bar W and D bar S are not the same in general, but if you assume that the form with which you start is good enough in terms of some Sobolev spaces, then the operators actually become the same. Maybe one last word. The d bar S equation this is the only missing slide that I just skipped. The L2 d bar S complex is exact in a point, in a singular point, exactly if the point is rational. So the d bar S equation, the strong d bar equation, is solvable in singular points if and only if it's a rational point. This is true. This is actually true for arbitrary singularities. So this is not just about isolated singularities. This is true for arbitrary singularities. Okay, and from this you get then these counterexamples here. So thanks a lot for your attention.